We're surrounded by things in constant motion. Water flowing through our pipes, fuel into our cars, steam powering factories. But have you ever stopped to think about how we actually measure all that movement? Well, today, we're going to open up the engineer's toolbox and take a peek at the clever devices that measure these invisible rivers. So here's what we're diving into. First, we'll talk about why measuring flow is such a challenge to begin with. Then, we'll look at the two main ways you can measure it, by volume or by mass. After that, we're getting hands-on with 3 specific tools. And finally, we'll figure out how an engineer chooses the right one for the job. Sound good? Let's get started.
Okay, so first things first. What's the big deal here? Why is this so tricky?
Well, think about it. It's not like you can just pop open a high-pressure pipe and dip a measuring cup inside, right? You've got to find a way to figure out what's moving on the inside, totally unseen. And that, it turns out, is a really interesting engineering puzzle to solve. And this is the hero of our story, the flow meter. This is the specialized gadget designed to do exactly that. It gives us the precise data we need, whether we're trying to measure a liquid, a gas, or even something like steam. So before you can even think about picking a tool, an engineer has to ask a really crucial question. What exactly are we trying to measure? The space it takes up, or the stuff itself? You really have 2 fundamental options here. The first is volumetric flow. That's basically asking, how much space is this stuff taking up as it goes by? You'd measure that in something like cubic meters per second. The other way is mass flow, which asks a different question. How much stuff, how much actual matter is passing through? And you'd measure that in kilograms per second. This little difference, as you're about to see, is a really big deal. And this image shows you exactly why it matters so much. Check this out. When you heat up a liquid, it expands, right? So its volume increases, in this case by 2.7%. But look at the scales. The actual amount of stuff, its mass, is exactly the same. It hasn't changed one bit. And that's the key takeaway here. When accuracy is absolutely critical, measuring mass is usually the better way to go because it doesn't get fooled by changes in temperature.
All right, now that we've got that fundamental concept down, let's open up that toolbox and look at 3 really common types of flow meters.
We're going to focus on a whole category called obstructive meters. And really, the name says it all. These devices work by putting something, a mechanical part, directly in the path of the flow. They literally get right into the middle of the action to figure out what's going on. First up, we've got a true classic, the turbine flow meter. The whole idea here is actually pretty simple and elegant. As the fluid moves through the pipe, it hits the blades of a little rotor and makes it spin, kind of like a high-tech pinwheel. The logic is simple. The faster the fluid is moving, the faster the turbine spins. On the outside of the pipe, there's a magnetic sensor that counts every single rotation, creating an electronic pulse each time a blade passes by. But, okay, how do you turn a bunch of electronic pulses into a real measurement, like liters or gallons? Well, that's where something called the K-factor comes in. This is a super precise calibration number. See, the thing is, even with amazing manufacturing, tiny, microscopic differences mean that no 2 meters are ever exactly the same. The K-factor is the unique magic number for each specific meter that translates those raw pulses into rock-solid, accurate data. And this isn't just some abstract idea. Check this out. This is a real factory calibration report. And you can see that this specific meter has a K-factor of 6,624.605. It's that incredible precision that lets an engineer completely trust the numbers they're getting from it. So, what's the bottom line? Turbine meters are fantastic. They're super accurate and they work great for clean liquids and gases. But they have their limits. You wouldn't want to use them for anything really thick, like syrup, or for dirty liquids, because that could jam up or damage the delicate spinning rotor. And they're not great for steam either. Okay, on to our next tool, which uses a totally different approach. This is the oval gear flow meter. Now, this one is based on a really cool principle called positive displacement. Instead of measuring speed, it measures volume directly. The best way to think about it is like a revolving door, but for fluids. You have these 2 interlocking oval gears. As they turn, they trap a tiny, very precise pocket of fluid between them and the chamber wall. Each full rotation shuffles a perfectly known amount of fluid through the meter. So you just count the rotations and you know exactly how much volume has passed through. Simple as that. So where does this meter really shine? Well, it's the go-to specialist for thick, goopy, high-viscosity fluids. Think oils, chemicals, even things like chocolate or molasses in the food industry.
It's super simple and very reliable. But here's the catch. It's not meant for thin fluids like water, and it definitely can't handle steam. Also, if you get air bubbles in the line, that can throw off the accuracy because it'll count a pocket of air just the same as a pocket of liquid.
And that brings us to our third and final tool for today. And this one is a real jack of all trades, the vortex flow meter.
Okay, this is seriously clever. Inside the meter, there's a small obstacle. It's called a bluff body that's placed directly in the flow path. As the fluid is forced to go around it, it creates these tiny alternating whirlpools or vortices on the other side. You know, it's the exact same reason a flag ripples in the wind. A sensor on the meter detects the little pressure changes from each vortex as it forms, and, well, it just counts them. The faster the flow, the more frequently the vortices are created, giving you a super precise measurement of the fluid's velocity.
And here is its superpower, versatility. The vortex meter is an absolute workhorse. It's reliable, it's accurate, and it can handle liquids, gases, and even steam, which, remember, the other two couldn't do. Its main kryptonite? Well, it doesn't like vibrations. If the whole pipe is shaking, it can mess with the sensor. And just like the turbine meter, it's not a fan of dirty fluids. So after looking at these three really different designs, it becomes pretty clear that it's all about choosing the right tool for the right job. Let's do a super quick recap. You've got the turbine meter, that's your high precision choice for clean, thin stuff. Then you have the oval gear meter. It's the undisputed champ for thick, viscous fluids like oil. And finally, the vortex meter. That's your flexible all-rounder, the one you grab when you need to measure liquids, gases, or even steam. Each one has a perfect spot in the engineering toolbox. So the next time you fill up your car with gas, turn on your kitchen faucet, or just think about how our world is put together, remember these amazing little devices. They're hidden away from the gas pump to the city water main, quietly and cleverly measuring the flow that keeps everything moving. Now that you're in on the secret, where else are you going to spot them?